Hello! Welcome back to the final lecture of this section. In this lecture, we'll explore a few methods to recover encrypted files, ranging from methods very specific to our sample to a more general approach that can be applied to many other samples as well. After file encryption finishes, a text box is displayed to the user where he is prompted for a password. This should be a clear sign that decryption is actually reversible. Although we can search for the strings visible in the image straight away in the code, unless you have a Russian keyboard, a good starting point is the data section we decrypted in a previous lecture. Notice that one of the strings corresponds to a successful decryption message. It only appears in one function at address 004.016 BC, which we've renamed as decrypt files for clarity. Notice in the image on the right that this function is in turn called only once following a string comparison operation. One string being compared comes from the dialog box retrieved by getDLGItemTextA function, and the other one comes from the decrypted data section, and its value is Q1W2E3R4. Try this password out and you'll see the sample will happily start giving back your files. One drawback of this approach is that we still don't understand perfectly what the sample does. There might be some hidden actions after the decryption process or some leftover backdoors that we would miss. This is not an uncommon tactic in the world of ransomware. Although encrypted in the data section, the decryption key was stored inside the sample. We relied on that password to let the ransomware decrypt itself. Since we know the details of the encryption algorithm, we will attempt to reconstruct the key initialization, encryption and decryption routine in a Python script and build ourselves a standalone decryptor. The full script can be downloaded and played with from the resources section. Re-implementing the algorithm in Python would be the quickest solution, but it poses a few challenges. We need to understand a bit of assembly code. We need to correlate that assembly code with online implementation of XT algorithm. We have to be careful when reconstructing a long number from an array of bytes, like the key array. Luckily for us, there are implementation of XT algorithm online, so we don't have to write it from scratch. We will play with this in the demo section next. Assembly and Python coding are outside the scope of this course, but if you're curious, definitely study the script or try to write your own. A much easier method that doesn't require us to understand the algorithm almost at all is to use Hexrace decompiler to extract the C source code and then build a separate decryption tool. Hexrace will produce source code similar with the one in the picture. On top of this, we need to add a function to read the encrypted files in 8-byte blocks and dump the decrypted blocks, and we're done. We will test this in the demo section. Writing C source code is outside the scope of this course, but this is an interesting and sometimes easier way to decrypt ransomware. Antivirus companies often write their own decryptors. This is actually the best way to verify your knowledge and make sure you have understood fully what the sample does. We've almost reached the end of our ransomware analysis, and luckily we have been able to recover our files. In this lecture, we've learned the following: how to locate a decryption password entered from a dialog box, how to write a standalone decryptor in Python starting from an online XT implementation, how to rip the encryption algorithm from the sample and reconstruct the decryption process without knowledge of the algorithm. So, next, we will see a demo for these two techniques. Make sure to try everything on your own virtual machine also. If needed, go back to the videos again and keep practicing. This is the best way to learn. Thank you for watching and see you in our next lecture.